What's up, guys? Welcome back to another video. As always,
wear your safety, guys. Number one priority.
Wear your safety. Goggles, glasses.
This stuff is
gloves.
dangerous. Come on now,
Be
remember.
careful. And remember, don't try this at home.
What? Guys, I'm pretty sure they can do this one at home.
Wait. They can do this one at home?
Yeah.
That's fantastic, guys.
Guys, we've got something for you today. No more sitting back. We've got an experiment you can really try. Video?
Yep.
That is sick, dude.
We gotta go.
Whoa, is that a Lloyd's mirror? That's awesome. Let me tell you guys something about these. So, you've got your typical single slit diffraction pattern. You can make that pretty easily with one of these gratings. But, some of us aren't able to get a double slit, so what we've done here is set up a Lloyd's mirror. And what this does is essentially turn it into a two-slit pattern. And we'll have a drawing that will explain. All right, so just to get some ground under us, lay the foundation, we're gonna talk about our standard single and double slit diffraction patterns. So up here, I have a diagram of a single slit diffraction pattern. And the way that this works is that the light coming through, one could come in through there and one could come in through the top, and there'd be an optical path difference, meaning each beam of light takes a different length to travel to its destination on the viewing screen. Because of this, and because light acts as a wave, when it comes in at different phases, it will either construct or destruct, causing bright and dark points on the viewing screen. Now, when you look down here, we have an example of a double slit diffraction pattern. And the way that this changes is that when you introduce two sources of light coming in, you still have your normal single slit diffraction pattern as seen by the overlay here, but the way that it appears, due to more light coming in with more, I guess, different paths, you get a much more separated diffraction pattern, which goes underneath where the single slit one would have been if there were not two slits. And so, now we can begin. So for the Lloyd's mirror experiment, what we did was take a single slit, as shown before, and added a mirror below. Now, as you can see, the light comes in into the single slit and it travels, say, path X along this line. Now, while some of the light is traveling straight there, also you have light that comes in and reflects off the mirror. After reflecting off the mirror, bouncing and hitting the same point on the viewing screen as this initial ray. Now, you can imagine this if you trace the light back from the origin, just hypothetically without a mirror in the way, it would be coming from here, resembling your double slit pattern. And because of this, while you can only get it on one half, of course because there's a mirror blocking the other side, you are able to create the same double slit pattern with only one slit and a mirror.
As you can see here, with the mirror out of the way, you can see a single slit pattern due to the wide fringes. And as we move it in, you can see here shortly that there are a bunch of dark fringes in between, demonstrating a double slit pattern made from our Lloyd's mirror. What up, guys? Welcome back to another application of Lloyd's mirror. We're gonna be looking at some microwaves here, very dangerous. So we have over here an emitter shooting out microwave rays. Boom, 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 boom. You can kind of hear it when you're up close. You really can't. And then you got a receiver over here, which is perfectly hooked up to this galvanometer, which will be reading an arbitrary gain value so we can get some data. This sheet right here will be acting as our Lloyd's mirror. As we bring it closer and further away at different distances, we'll be able to see different values and we'll be able to plot them to hopefully indicate something, guys. Isn't that kind of crazy?
What are you going to indicate?
What am I going to indicate? To be determined. Moving the mirror to different distances and gathering the different gains being read, a graph of the gain reading versus distance can be made, which demonstrates the optical path difference the microwave rays make, which creates an interference pattern that can be seen through the graph.
All right, welcome back. So here, as you can see, we've got a Lloyd's mirror apparatus set up with a sound detector and a sound maker. And now we're pumping out sound at a constant 20,000 hertz. So what we're gonna do is we're gonna slowly raise and lower this jack. By doing that, we're creating essentially another disturbance pattern. No, it's an interference pattern. Like we saw with the laser over there, we'll get another interference pattern.
Okay guys, we're going to be needing some key measurements here to calculate some optical path differences that the sound takes here. One measurement we're going to need is the distance from the emitter to the receiver. We roughly have it around 41 centimeters. Another distance you'd like to be gathering is for each local max or min you find from the sound interfering, you'd like to find the height it's at to whatever 0 point you have established. So as you're going down or up, and there's a max or min here, take that point down. Another distance you'd like to have is the distance from the bottom of your phone emitter to the top in order to calculate that optical path difference. And in order to calculate that, you can simply just do Pythagorean's theorem to find the distance. It goes from the bottom to your receiver and from the top of your emitter to the receiver. And from there, you can establish a graph. By finding the differences in the two hypotenuses, a graph of the optical path difference can be made. Each dot represents a local min or max as the height increases. And as we all know, a straight line is always a good thing. Have a good one, folks.